This video is for ELEC 1510 Logic Design. This is Lecture 11, Part 2 on Carry Lookahead logic, corresponding to textbook section 4.5. In this slide, we see the 3-bit adder that was constructed in the previous lecture video. We have inputs x with 3 bits x2, x1, and x sub naught. Input y with 3 bits y2, y1, and y naught. Output s with bits s2, s1, and s naught, and a carry out bit. One problem with the circuit is that the calculations cannot all happen at the same time. For example, if we want to use this full adder to calculate S2 right here, we need the value of the carry out from the previous full adder. That means that the calculations in the previous full adder must run first before we're able to calculate S2 from this full adder. However, one of the inputs to this full adder, the carry in, is dependent on the full adder carry out from the previous stage. Therefore, every full adder in the chain is dependent on an output from the previous full adder, meaning that not all of the operations in this big module can happen at the same time. So ultimately, it's much better to produce two-level logic that produces all of the carry-in inputs, here, here, and here, for each full adder as a combination of the current inputs only, and not of anything produced by any full adder that could be more than a two-level circuit. This type of construction, where the carry in to every full adder is a function only of the current inputs, is called carry lookahead logic. In this slide, we see an alternative model for a full adder made of 2 half adders. This is more complicated than the full adder circuitry that I derived in the previous video, but it's convenient for carry lookahead logic. There are 2 intermediate variables produced in this construction, P sub I and G sub I, which stand for the carry propagation and the carry generation. The sum for each full adder and the carry out for each full adder can be written as a combination of P sub I, C sub I, and G sub I, which are the carry propagation, the carry generation, and the carry in for each stage. The index I, used here as a subscript, just denotes which number full adder you're using. You can use full adder 0, 1, 2, 3, depending on how many bits you have in your adder circuitry. Now you can see from this part of the diagram that carry sub I plus 1 is going to be equal to P sub I, the carry propagation from the previous stage, times C sub I, the carry from the previous stage, plus G sub I, the carry generation from the previous stage. So this means, for example, that the first carry bit, so this is the carry out of the very first stage, is going to be equal to P sub 0 times C sub 0 plus G sub 0. So that means that the carry out of the first stage, or the carry in to the second stage, is equal to the carry propagator from the first stage times the carry in to the first stage plus the carry generation from the first stage. Now, the second carry is going to be equal to P sub 1 times C sub 1 plus G sub 1. And now we can substitute the value of C sub 1 here into that equation to get P sub 1 times P sub 0, C sub 0 plus G sub 0 plus G sub 1 for the complete expression. that could be expanded out basically into a sum of products expression. Now C sub 3 would be P sub 2, C sub 2 plus G sub 2, and we would enter in the sum of products expression for C sub 2 into this expression to get a fairly long sum of products expression that I won't write here. So now every carry in for each full adder is a sum of products expression that depends only on the P sub I factors, the carry propagations, the G sub I's, the carry generators, and C sub 0 ultimately, which means that they can be written with the same number of levels for each carry in to each full adder, so there's no delay between the calculations for each carry in. In this slide, we see the carry lookahead generator circuitry that I had derived the equations for in the previous slide. So where C1 here is formed as a combination of P0, G0, and C0, C2 is formed as a combination of P1, G1, and these previous variables. C3 is formed as even a more complicated circuitry of P sub 2, G sub 2, and these variables and these variables. If you went to C sub 4, C sub 5, etc., it would just get more and more complicated. So this is called carry lookahead generator. All of this can be written just as a block of circuitry, and we can use this block of circuitry to construct a complete multi-bit adder circuit. And we see that here, a 4-bit adder with carry lookahead. This carry lookahead generator is the circuitry that we saw in the previous slide. It has inputs P sub 0, G sub 0, C sub 0, P sub 1, G sub 1, etc. Outputs the carries for each stage. And so therefore we need to generate P sub 0 and G sub 0 and all of the other P and G variables by using half adder blocks, as you see there. And then the sum outputs can be constructed as a combination of the carry outs and the P sub I variables. And what this does actually is it produces a big 4-bit adder circuit where all of the operations can run at the same time. None of the operations depend on logic with more levels than any other operation, so you don't have problems with delays and operations that need to occur before other operations and things like that.